The information presented in the previous tutorials includes the structure's shape and properties as well as the loads imposed on it. The results section shows the resulting forces distributed to each shear walls, and the main results are separated into two main categories: wind design and seismic design. In the wind design tabs, the results are separated into the following subcategories: flexible diaphragm design, rigid diaphragm design, and components and cladding by shear line. The flexible and rigid diaphragm analyses are both available in the results for wind and seismic. The loads are not distributed in the same way for both methods, thus it is important to consider both cases, as it is hard to predict for some structures whether it will act as a flexible structure or a rigid structure. For the flexible diaphragm analysis, the loads are distributed assuming that the building faces are simply supported by the shear lines, which acts as pin supports. Therefore, the load is distributed based on tributary width. The rigid diaphragm analysis distributes the shear forces according to the relative stiffness of the shear walls and the torsional behavior of the rigid diaphragm. For more information on the flexible and rigid diaphragm analyses, refer to the online tutorial entitled Tutorial 4 Flexible and Rigid Diaphragm Distribution. For each of the wind and seismic, flexible and rigid section, the resulting forces within all shear lines are shown, including the results for shear, hold-down design, drag strut forces, deflection, and hold-down displacement. The last two, deflection and hold-down displacement, are only available when the Include Deflection analysis is checked in the design settings. For simplicity, only the tables for the flexible analysis will be explained, as they are the same for rigid analysis but with different values. Let's look at the wind results. The shear results for wind are accessed by the following: Go to table, wind design, flexible or rigid diaphragm design, and then shear results. The results are separated into two main groups: the north-south shear lines and the east-west shear lines. The shear lines within a direction are further classified in ascending order, and within each shear line they are further classified by their respective elevation or level in a descending order. If there are multiple walls within a shear line, they will be presented separately. To create multiple wall segments within a shear line, we first have to select the walls icon in the toolbar and then draw a wall segment over an existing wall. Now run the design and go to the flexible diaphragm design for wind shear results. As you can see, for line 1 level 1, the different walls are presented separately. Beside the name of the wall or shear line is the wall group as listed in the sheathing and framing materials table. Coordinating the wall groups with the different walls on the shear lines is important, as it allows to see which wall group works for this particular load result. A legend is available at the bottom of the table with all the definitions of the term, but a quick review of these terms will be done from left to right. If the generated force is the same in both directions, both will be written, and if not, the results for the wall for both directions will be indicated separately. To the right of the force direction is the fiberboard height to width factor, also known as the fiberboard aspect ratio factor for wind, from the following table. And or the unblocked structural wood panel factor from the following clause. The aspect ratio is the maximum height to width ratio allowed for different materials in order to consider the contribution of the wall segments to resist the shear forces applied to the building. If the maximum height to width ratio is exceeded, no force is allowed to that segment, therefore ignoring its contribution to shear resistance. Some materials have a conservative height to width aspect ratio, but it allows you to increase it if the capacity is decreased. The decreased capacity is achieved by what we call the aspect ratio factor as per the following table. For wind design, the only height to width aspect ratio factor applicable is for fiberboard walls. Fiberboard shear walls are not considered to contribute to shear resistance if their height to width aspect ratio exceeds 1 to 1 unless the nominal unit shear capacity is multiplied by the aspect ratio factor for wind specified in Note 3 of Table 4.3.4. To save space, the height to width aspect ratio factors and the unblocked factor CUB were combined in the same column as they never occur at the same time due to the fact that the aspect ratio factor only applies to blocked walls. Therefore, proper attention must be given when interpreting these values as they could stand for two different factors for the two surfaces. The int stands for the interior sheathing of the wall, and x stands for the exterior sheathing of the wall. I will demonstrate a few examples of how the value of the factor changes depending upon the material and height to width ratio. For a wall consisting of structural fiberboards on both sides with a height to width ratio greater than 1 to 1, the factor will be equal for both the exterior and interior columns. First, we will select the three wall segments, deselect the Design and Group option, select both sides the same, apply half-inch fiberboard, with edge spacing of 4 inches and field spacing of 12 inches. We will now run the design. As you can see, for the three wall segments of line 1 level 1, the interior and exterior factors are the same on both sides and in conjunction with the following table. As you may have noticed, little shear force has been allocated to wall 1-1 and wall 1-2, even though their maximum height to width ratio do not exceed the one specified by SPIDWIZ. This is due to the fact that the Include Deflection Analysis tab in the Design settings is selected. We will remove this option, select the Use Shear Wall Capacity to approximate rigidity, and distribute forces to wall segments based on rigidity, and then rerun the design. Now, as you can see, shear force has been allocated to these two segments. For a blocked wall with fiberboard on one side and gypsum on the other, with a height to width ratio smaller or equal to 2 to 1, the factor will be equal to 1 for the side of the gypsum, and for the side of the fiberboard, it will be equal to the value determined by the following table. To illustrate this, we first have to select the walls icon and edit the walls. Deselect the both sides the same. The exterior side will have fiberboard, while the interior side will have half-inch gypsum. We will now run the design. As you can see, for the interior side of wall 1-1 to wall 1-3, the factor is 1.0, and for the exterior side, the factor is determined as per table 4.3.4 shown earlier. Now, if we have a wall consisting of gypsum wallboard on both sides with a height to width ratio that exceeds 2 to 1, zero force will be allocated to that segment. First, we have to select the walls icon in the toolbar, and then we will edit the dimensions of wall 1-1 so that it exceeds the 2 to 1 ratio. A dimension of 3.5 should be sufficient. We will now select all 3 wall segments and apply 1/2-inch gypsum on both sides. We will now run the design. Keeping the same wall, but having it unblocked and the height to width ratio greater than 1.5 to 1, we will see that 0 force will be allocated to that segment. We will first select the walls icon and select wall 1, 2, and change its end location to 8.5 feet. So it has a height to width ratio slightly above 1.5 to 1. We will select all 3 wall segments and deselect the blocking option. Run the design. As you can see, 0 force has been allocated to segment wall 1, 2. It is important in order to observe these results that the disregard shear wall height to width limitation is unchecked in the design settings. In addition, make sure that the material used are allowed within the seismic design category, which can be seen in the site information.